During a demolition derby, a green car is moving at a constant speed of 13 meters per second. 85 meters away, a blue car starts toward the green car at a rate of 4 meters per second squared. How far from the green car will the two cars smash into each other? The picture is drawn. We have our green car here on the left. We have our blue car on the right. The green car is moving at a constant 13 meters per second, which is why we only need D, V, and T, because there is no A for that car. For the blue car, the acceleration is to the left, 4 meters per second squared. That's why it's a negative 4 meters per second squared here when we write down our variables. And the initial velocity is 0, but it is getting faster and faster and faster. We're trying to find where they're going to crash, and that's when they're at the same spot. So we want the position for each of the cars. That's why those are the question marks. We have to use two different equations here. For the green car, we have constant velocity. So the only equation we have to work with is D equals V times T. If I plug my numbers in, I only have one number, and that's 13 meters per second. For the blue car, I'm going to pick the equation that does not have final velocity in it because the displacement and the time are actually going to be the same for the blue and the green car. Since they share that in common, that's what I'm going to use. So for the blue car, D equals V naught T plus 1/2 A T squared. If I were to plug in my numbers for that, V naught T is going to cancel, and that's going to leave me with D equals 1/2 times -4 times T squared. But we actually have to add one more thing to that blue equation, and that's we have to account for the fact that the blue car starts 85 meters to the right. So we have to add 85 meters to both equations. Now the equation is done. What we're going to do is I'm going to set this 13t equal to 1/2 times -4t squared plus 85 because I want the positions when they're the same. Easiest thing to do would be to solve for time and then use that to plug back in and solve for d. So what that's going to give me is 13 meters per second times t equals 1/2. 1/2 times -4 is just -2 times t squared plus 85 meters. Now solving for t straight away is actually going to be very difficult because this is a quadratic. We have a t and we have a t squared. So we have to rearrange this into our quadratic formula. To do that, I'm going to move the 13t over because the quadratic formula basic equation is 0 equals ax squared plus bx plus c. So I'm going to rearrange this so that it looks something like that. So we get 0 equals -2 meters per second squared times t squared. Then it would be minus 13 meters per second times t plus 85 meters. The -2 is my a. -13 is b. And 85 is c. And if you remember the old quadratic formula, the quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac all over 2a. This is my a value, so everywhere I see an a, I would plug in -2. There's my b, which is -13, and my c is 85. And this is all going to be t is acting as my x. So negative b, which would be -13 or 13, plus or minus -13 squared minus 4 times the a is -2, and c is 85, all over 2 times -2. If I plug all of that into my calculator, I'm going to get two possible answers. I would get time equals -10.53, or it equals 4.03 seconds. We don't ever want to use negative time, so this is the time that I want. So from here, I can plug back in to either of my basic equations. I'll just plug into the easiest one, which is the green over here. You can see I'm just going to plug right back into that equation. And that's going to give me the location where they're going to crash is 13 meters per second times the t, which is 4.03 seconds. And that gives me a location of them crashing at 52.45 meters.